Now we can move on to covalent bonds. Before we do this, I want to go over some things that we already know about bonding and ionic bonds. Using the Lewis model, atoms bond together in such a way that each atom acquires a valence shell electron configuration of the noble gas of 8 electrons. We know there's two main types of bonds, ionic and covalent. We know that ionic bonds form bonds between atoms with the loss or gain of electrons to acquire the electron configuration of the noble gases. So sodium loses an electron and chlorine gains an electron to reach the noble gas with 8 valence electrons. Sodium has 1 valence electron and chlorine has 7 valence electron. Sodium loses an electron, chlorine gains an electron to give a compound with a bond where sodium has an electron valence configuration of neon and chlorine assumes a valence electron configuration of argon. They do not share electrons, but there is a bond between the two atoms that is an electrostatic bond, where the two atoms are held together by the attraction between the negative and positive charges. So the ionic bond would look like this, where no electrons are shared, but there is an electrostatic attraction. Let's move on to covalent bonds. Covalent bonds share electrons to assume the electron configuration of the noble gas. A good way to describe a covalent bond between two atoms is with the simplest atoms, hydrogen. Here we have hydrogen with 1 valence electron on each atom, and when a covalent bond occurs, the valence electrons are shared. So looking at the periodic table, we have 2 hydrogen atoms, which is right here. So when there's a bond between 2 hydrogens and the electrons are shared, the electron configuration reaches the noble gas state of helium. Let's look at some more diatomic molecules that are covalently bonded. Here we have nitrogen, which is right here on the periodic table. And nitrogen is in group 5A, so it has 5 valence electrons. So in order to reach an octet, it would have to gain 3 valence electrons. So this is done by sharing 3 valence electrons with another nitrogen, and together they make 3 bonds to reach the noble gas of neon, which would have 8 valence electrons. Here you can see that the diatomic molecule shares 6 electrons, and each atom shares the 6 electrons. So this atom shares 6 electrons, and this atom shares 6 electrons, which would give it a full octet. Let's take a look at another diatomic molecule that's covalently bonded, which is diatomic fluorine. The element would be found right here on the periodic table, and fluorine is in group 7A. So to reach the noble gas configuration of a complete octet, it would have to gain 1 electron. So fluorine right here needs to gain 1 electron to get to the noble gas configuration of neon. And you can see the fluorine has 1, 2, 3, 4, 5, 6, 7. And with covalent bonds, all the bonds that are shared count towards getting to the noble gas. So this fluorine would count all of these electrons that are shared, giving it a full octet. So it would have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. And this fluorine atom would do the same thing. It would count both electrons that are shared, 1, 2, 3, 4, 5, 6, 7, 8, to give it the electron configuration of the noble gas. For ionic bonds, like sodium chloride, will not share an electron, but an electron is completely transferred from one orbit to another, from the sodium atom to the chlorine atom, for each atom to gain an electron configuration of the noble gas. So far we've described ionic bonds and covalent bonds, but we've described this through a subatomic lens to give a more quick and general way to determine whether or not a molecule has bonds that are ionic or covalent is by looking at the periodic table. On the left side we have metals, and on the right side we have nonmetals. This black diagonal line separates the metals from the nonmetals, and these elements along each side of the diagonal line are what are called metalloids. And a quick and general way to determine whether or not a bond is ionic or covalent is by determining whether an atom is a metal or a nonmetal. So metals bonded with nonmetals will generally have an ionic bond, and nonmetals bonded with the nonmetals or metalloids will generally form covalent bonds. Covalent bonds share electrons. Sometimes they are shared equally, sometimes they are not shared equally. To explain why they may or may not be shared equally, we need to understand electronegativity. Electronegativity is an atom's ability to compete for electrons with another atom. This is a periodic property that depends on the nuclear charge and the distance of valence electrons from the nucleus. This can be explained in two ways. The number of energy shells between valence electrons and the nucleus, and Coulomb's law. We have somewhat of a good idea of what the shells of an atom are, so let's look at Coulomb's law. Coulomb's law says the magnitude of the attractive or repulsive electrostatic forces between 2 point charges is directly proportional to the product of the magnitude of the charges, and that would be this portion of the equation, and inversely proportional to the square root of the distance of them, which would be this portion of the equation. This is a very fancy way to say when 2 point charges increase, the electrostatic force will increase, and when the distance between the two charges increases, the electrostatic force will decrease. This is very intuitive when you think about a magnet. The bigger the magnet is, which would be the charge, the more of a repulsive or attractive force it has. And the further away you would have the two magnets, the more it would decrease the force. Now let's take a look at the periodic table and the trends that the periodic table has with electronegativity. We can see as we go up the column, the electronegativity increases, and as we go from left to right, the electronegativity increases. So when we go left to right, the number of protons and electrons increase. So we know from Coulomb's law that when the magnitude of the point charges increases, the attraction or repulsion will increase. Moving to the second period, this becomes more obvious. Where lithium would have 3 protons and 3 electrons, and fluorine would have 7 protons and 7 electrons. So fluorine would have a much greater attractive force than lithium. Going up the column, we can see that electronegativity increases, and this is because the distance decreases as we go up the column because of the shells. Where period 1 would have 1 shell, period 2 would have 2 shells, period 3 would have 3 shells. So these valence electrons at the bottom would be much further away than the valence electrons at the top. And we know from Coulomb's law that as the distance increases, the force will decrease. Another point to consider at the bottom of the periodic table, there are several shells in between the electron and the proton. And another way to think of a shell is a cloud, like a misty cloud of a negative charge. And the negative charge of this valence electron has to pierce through each one of these layers that repels the electron, which would make the force decrease. Alright, so let's sum up what we know about electronegativity. We know that electronegativity increases as we go up the column and from the left to the right. We know as we go from the left to the right that the electrons and the protons increase, which would increase the point charge. And we know from the Coulomb equation that as the point charges increase, the attractive or repulsive forces increase. In this case, it would be the attractive force. And we know that as we go up the column, the number of shells decrease, which would decrease the distance between positive proton and the negative electron. We know from the Coulomb equation that as the distance increases, the attractive force will decrease. So in this case, the distance decreases, so when it's closer together, there's more of an attractive force. Along with Coulomb's law, we know that the shells play a role in the attractive forces. Because an electron on the outer valence shell, it has to go through several layers of a cloudy mist or a cloud of electrons or layers of electron. It effectively slightly cancels out the attractive force with each layer that it has to go through, because each layer has a misty cloud of a negative charge, and the negative charge would cancel out the positive charge. Here's a diagram that describes a more visual size difference between the atoms, and we can see that, and this only goes to sodium, but they get bigger as we go down the group. We can see that sodium is a big metal, so it has 3 shells, and it just would not be as electronegative as a non-metal, where it would have an abundant amount of electrons and protons that would increase the total amount of point charges, like fluorine right here. And you can see that there's a lot of electronegativity because they're so small. What that means is the protons are pulling the electrons in towards it because there's so much attraction from all the point charges that don't have to go through all the layers of shells that metal like sodium would have to go through. Right here is a diagram of bonding where these 2 dots would be just arbitrary atoms. The dotted line would be the line between repulsion and attraction, which would be at the bottom. And you can see that when atoms get really close together, they start to repel. As they get further apart, they fall into a zone where it's just perfect to bond. And then as they get farther apart, they just don't have enough attraction to pull in the other atom to bond. And what's happening is the positive nucleus or the positive proton of one atom has an attraction to the electrons of the other atom, and it wants to pull it in, and vice versa, where the positive protons on the other atom would have an attraction to the electrons on the other atom. When these would reach the perfect distance, then they wouldn't be too far away and they wouldn't be too close, and they would bond. What happens is when they're very close, like these 2 atoms up here, what starts to happen is these protons will repel these protons. So the protons from one atom will start to repel the protons from another atom. Before we move on, I wanted to briefly talk about some definitions that you may have heard of that are similar to electronegativity, which is electron affinity and ionization energy. I'm just going to draw a generic atom here to illustrate what this is. Electron affinity describes the ability of an atom to attract an electron, and ionization energy is the energy required to remove an electron from an orbit. What these are talking about comes from the framework of a single atom or an individual atom, whereas electronegativity is in the framework of a molecule. So if we had hydrogen chloride, the electronegativity would mostly be on the chloride atom, and it would want to pull most of the electrons towards the chlorine, where the chlorine would have the lion's share of the electrons. When we measure the quantity of an atom's electron affinity, the ability to attract an electron, and an atom's ionization energy, we then have a good idea of how that atom will compete with other atoms. It is only after we consider both of these properties of ionization energy and electron affinity that we can then measure and determine the electronegativity. An example would be fluorine and chlorine, where chlorine has an electron affinity that's actually higher than fluorine, but when we consider the ionization energy, fluorine has a much higher ionization energy than chlorine, and when we add both of these up, we then get the electronegativity, where fluorine would have a higher electronegativity than chlorine. To sum this up, electron affinity is the ability to attract an electron. Ionization energy is the amount of energy that's required to remove an electron. These are properties of a single atom. When we add both of these properties up, we have the electronegativity, and the electronegativity is the ability to compete with other atoms to attract electrons in a molecule. So when an atom can attract electrons to it, and when an atom can hold an electron in its orbit, those add up to good electronegativity, and that atom will compete very well when it comes to competing for electrons with other atoms. Here's a periodic table with the electronegativity of each atom. A general rule to go by is when the electronegativity difference between bonded atoms is less than 0.5, then it's a nonpolar covalent bond. Between 0.5 to 1.9, it's a polar covalent bond, and anything greater is considered to be ionic. So let's look at a few molecules to see what the electronegativity difference is. So if we look up sodium, we can see the electronegativity is 0.9. If we look up hydrogen, we can see the electronegativity is 2.1. So to find the difference, simply subtract 2.1 minus 0.9 equals 1.2, and this falls in the polar covalent category. So this is polar covalent, so this would have a difference of 3.1. So you can see this is clearly ionic because it's greater than 1.9. This would be more polar than this, HCl and OH. So chlorine is 3. We get the difference by subtracting hydrogen. Electronegativity is 2.1. So we have 0.9. And looking at the chart, it looks like it falls within 0.5 to 1.9. So it would be polar covalent. So this is polar covalent. Next we have oxygen, which is 3.5 minus 2.1. We have 1.4. And this looks like it falls in the polar covalent because it's in between 0.5 and 1.9 at 1.4, so it would also be polar covalent. Just an example of a non-polar covalent molecule, we had diatomic oxygen, so 3.5 minus 3.5 be obviously 0, and that is less than 0.5, so it's nonpolar. Some other examples of a nonpolar covalent bond might be CH4, so carbon be 2.5, and hydrogen is 2.1, so we would have 0.04, and that would be less than 0.5, so it's nonpolar covalent bond. I want to go into these three categories where it's nonpolar, polar, and ionic. I'm just going to put non-P, P, and ionic over here. And we describe this as molecules were either 100% ionic or 100% covalent. And what actually happens is the more we go from the left to the right, it becomes ionic, where 100% ionic would be where an electron transfer goes from one atom to another, and there's an electrostatic charge where it takes an electron completely out of the orbital. And on the other end over here would be the ideal covalent bond where electrons would be perfectly shared equally. The reality is neither one of these extremes really exist, but they're more of an gradient to where nonpolar covalent bond, it has a lot of character where they are shared equally, and as we go over to the ionic part of the spectra, that it would have more ionic character. So there is no binary category where it's either ionic or covalent. It's a spectrum, and it does go back and forth here where it can have a certain percentage of covalent character and a certain percentage of ionic character. A chemical species in which there is a separation of charge, there is a positive pole on one part of the species and a negative pole on the other part, is called a dipole. The more we go from nonpolar covalent to ionic, the more of a dipole will develop on a molecule. This is an electron density map that shows a high density of electrons in the red and a low electron density in the blue. So hydrogen would have less electronegativity than chlorine. Chlorine would pull the electrons in closer to it, and it would have a high electron density in that area. The partial positive and partial negative charge on a molecule is denoted by the lowercase Greek letter delta.